All right, so the SN1 reaction is the exact opposite. Everything that we just learned is going to be the exact opposite. Tertiary alkyl halides react faster. Okay, we're not going to worry about the solvents, so don't even worry about the solvent effects. Okay, your book talks about it, but we're not going to talk about it. Tertiary, excuse me, halides react faster, and you also need a weak nucleophile. Notice we have a weak nucleophile. We have water instead of hydroxide. Okay, and this is called an SN1 reaction because it occurs in 2 steps. I know it's kind of confusing. You think, well, if it's SN2, shouldn't that be 2 steps? Well, the mechanism just depends on the concentration of our electrophile. All right, so the rate equation in this case, the rate equals a constant times the concentration of the electrophile. Not the nucleophile this time, just the electrophile. It depends on how quickly your leaving group leaves. Okay, if your leaving group leaves quickly, the reaction goes quickly. If the leaving group leaves slowly, the reaction goes slowly. Okay? This reaction happens in 2 steps, so it is a stepwise mechanism rather than a concerted mechanism. Okay? And if nucleophile is present in a reasonable concentration, then ionization is the slowest step, which is what we just said, because the whole rate is dependent on the electrophile. Okay, now in this case, it's the exact opposite. In this case, tertiary is going to be the fastest, followed by secondary. And again, primary isn't even going to go. The reason is because you form a carbocation in the intermediate. Carbocation intermediate. Intermediate. Okay, so because of the carbocation intermediate, we've learned that making a mess here. That tertiary carbocations are much faster or more stable, so they form, followed by secondaries and so forth and so on. Okay. So the overall reaction is controlled by the slowest step, which is the leaving of the alkyl halide. So it depends on the concentration. So the rate depends on the concentration of the species and the rate constant of the step. The SN1 reaction is unimolecular. So the first part, the rate constant on the step means however quickly the bromine leaves, that's what the rate's dependent on. The rate depends on the concentrate of the substrate. That's what I just said, the electrophile. The substrate must undergo a reaction without an involvement of the nucleophile, and you need weak nucleophiles. Okay? So what happens here? What happens here is your leaving group leaves first, and you form a carbocation. Okay? So you'll have your plus charge. And this is now planar. Okay? So right here is the intermediate. Now, since you've formed a plus charge and you form a trigonal planar compound, your nucleophile can attack from either side. There is no preference. So because of this, if you start with a chiral compound, your final compound is racemic. You guys remember what racemic means from the chiral chapter? That means you have a 50-50 mixture of enantiomers. All right, so 50% of it is a nucleophile attacking this side, the other 50%. Even if you start with a chiral compound, right? Even though this compound is chiral, all right, once this leaves first, you now form an achiral intermediate, which now your nucleophile can attack either side. So you get racemization with an SN1 reaction. Okay. The leaving groups very similar to SN2s. You know, your halogens really are the best leaving groups. Okay. Water, like I said, we've learned water in one of the reactions previously with the alcohol is a good leaving group. We're not going to talk too much about it in SN1s, but pretty much the leaving group is the same as in SN2s. Okay. So what we'll do in class is we will definitely talk a lot more about SN1s and SN2s. I just wanted to kind of give you an introduction to it so that you have an understanding of it, and we will definitely talk more about it in class. Okay. The next reaction is an elimination reaction. Okay, and again, it's going to go through either a unimolecular mechanism or a bimolecular mechanism. Okay, and it really depends on the strength of your base in this case. Okay, but an elimination is an alternative pathway to substitution. Okay, it's the opposite of addition, obviously. We're going to form a double bond. So this is the reaction that we're going to look at now. This is SN1, SN2s. Okay, now we're going to look at eliminations. Now, one thing that your book doesn't do, which I will talk about in class, is the base. This is the base. Okay, now you need a bulky base for this. The larger the base, the more elimination product you're going to get. They don't really have a bulky base, but I'll talk more about this in class and on the videos. This slide though talks about what's called Zaitsev's rule. Okay, Zaitsev's rule of elimination. Basically, it says if you have a compound, and I'm going to eliminate this. Eliminating means I'm going to pluck a hydrogen off of a neighboring hydrogen. Let's go to the previous slide just to kind of show you what the reaction is. But pretty much what happens is your base, in this case it's hydroxide, is going to pluck off this hydrogen. These electrons go into here to form a double bond and kick out the bromine. So in order to have an elimination, you need to have right next door. So here I have a carbon and my halogen. The carbon directly next door to it has to have a hydrogen on it. Okay, it's what's called a beta hydrogen, because this is the alpha carbon with the halogen on it. This is the beta carbon, so therefore the beta hydrogen is attached to the beta carbon. You have to have a beta hydrogen. You have to have a hydrogen next door to your halogen to have an elimination reaction. Okay, well, in this example, notice I've got a hydrogen on this side and I got a hydrogen on this side. So I have two beta hydrogens. Okay, so I have this beta hydrogen, so let's call this the A hydrogen. Let's call this the B hydrogen. So if my base were to pluck off a hydrogen over here, I would form a double bond between the A carbon and the carbon that has the halogen. Okay, so that would be this compound right here. Right, here's the A carbon right here. We're plucking off one of these hydrogens. If I form a double bond here, this is right in the middle, it'd be this compound. So that would be the B hydrogen. Okay, so we have two possible products, but notice 80% of it is this one. All right, it's where you're plucking off the hydrogen at the more substituted position. A lot of people would think, well, wouldn't it make sense if you pluck it off at the least substituted? Yes, that would. But what Zaitsev's rule is that the product with the more highly substituted alkene is the one that predominates. So which of these double bonds is more substituted? Remember, we have a primary substitution, a mono substituted double bond, which would be a double bond with one carbon and three hydrogens. That's mono substituted. Di substituted would be two carbons and two hydrogens. Tri substituted would be three carbons and a hydrogen. And finally, tetra substituted, sorry, Mr. Butterfly, that would be tetra substituted, where you have four. This is more substituted, this is next, and so forth and so on. So in this case, this double bond is di substituted. Why is it di substituted? This carbon's attached to this carbon, and this carbon's attached to that carbon. So that's di substituted. This is mono substituted. I got this carbon is just attached to this carbon group. It has a hydrogen and two other hydrogens. So that is mono substituted. So the one that makes the more substituted double bond, which is this one, is going to be my major product based on Zaitsev's rule. So anytime you do an elimination, the major product is going to be the one that's more substituted. So if we look at this example, we actually have hydrogen here, hydrogen here, hydrogen here. But these both form mono-substituted products. This forms actually a tri-substituted. Notice you have a tri-substituted. And if you look at the percentages, you form quite a bit more, even though you have twice the amount of elimination product possible over here. Okay, so it doesn't matter if this is E1 or E2, you will always get Zaitsev's rule. Okay? So let's talk about the mechanism. Okay, first let's talk about the E1. Eliminations can take place by several different mechanisms. Okay, for the E1, what happens first is your leaving group leaves first, and forms a carbocation. So what do you think, what type of carbon would be the fastest for this? A primary, a secondary, or a tertiary? Since I'm forming a carbocation, if you said tertiary, you are correct. Tertiaries go faster than secondaries, and basically you won't even go primaries. Okay, that's for an E1. Okay, form a carbocation, then your base comes in, plucks off the hydrogen, and forms the double bond. Okay, E2, it doesn't matter. It doesn't matter if it's primary, secondary, tertiary. These equally, actually it's not true. Believe it or not, a tertiary actually goes faster than a secondary, goes faster than a primary. The reason is because it hinders this carbon. Remember we said, so there's a competing reaction versus E2s and SN2s because I have a strong base, right? Let's say I have a strong base. Well, I just told you, if I have a strong base in an alkyl halide, there's a really good chance it can actually attack the carbon and kick out and I get a substitution reaction. Well, if this is substituted, if this is so hindered that my nucleophile can't squeeze in there, it's going to grab one of these hydrogens instead. Okay? So imagine if I have a really substituted, I'm probably going to run out of room here, but imagine I have a really substituted alkyl halide and I have, you know, a base, a strong base. It can't squeeze in here. It can't squeeze in and attack this carbon. It can't get in there. So instead, it's going to pluck off one of these hydrogens here and form a double bond and kick out my bromine. Okay, so that's why tertiary actually in E2 actually goes faster. But, you know, if you just want to say it's equally, I'm fine with that. There is no preference in this case. But this is concerted. This grabs the hydrogen makes the pi bonds, and your halogen leaves. Okay, so here is the mechanism in full glory. You can kind of look at this. We just talked about this. It's bimolecular. Okay, as this attacks, pops down, kicks that out. It kind of shows you this, the whole transition state all at once. All right, so the E1, we've already talked about this, but we'll talk about it again. It involves a carbocation intermediate. So first the halogen leaves to form a carbocation, and then your base comes by, plucks off the hydrogen. So same type of mechanism, but your leaving group leaves first. And in this case, obviously, you're going to want a tertiary greater than secondary, greater than primary, because we're forming a carbocation right there. So here's kind of a summary of everything, okay? And I'm going to go over some summaries in class too, but this is a pretty good summary of everything. Okay, primaries. So if you have a primary alkyl halide, SN2 reactions occur the best. Okay, and you want really good, strong nucleophiles. All right, anything that has a minus charge. We didn't really talk about ammonia, but ammonia is actually a pretty strong nucleophile. Okay, E2 eliminations also occur if you have a strong, bulky base. I didn't talk too much about it, but hydroxide is not good enough of a base. I don't know why your book talks about this. The base that I use when I do an E2 is called tert butoxide. It's a very hindered base. This is the base I use for elimination reactions, and that's the base I want you to use. So if you do an elimination reaction, this is what you want to use. You don't want to use hydroxide. That's too small. Okay? Way too small. Okay? You want to use a big, bulky base. Okay? E1CBs, we are not going to talk about, so don't even worry about that. Okay? Secondary alkyl halides, SN2s, E2s, SN1s, E1s all occur. They don't really talk too much about it, but they can. And again, we're going to get rid of this. You can also do SN1s. We'll talk about it in class a little more. E1, if you have weak nucleophiles. Weak nucleophiles, you'll do SN1s and E1s. Strong nucleophiles, you do SN2s, E2s. Okay, for tertiaries, E2s, E1s, and SN1s. We're not going to worry about the E1CBs. Okay, so that's a good summary of everything.